Hi, guys. There's a lag. Shoot. How you guys doing today?
Good.
Not bad at all. How about you?
Good, thank you. We'll just give it a second, see if other people are going to. Yep. Good. So I realized in my lecture examples for 3.5 that I forgot an example. So I have an example 0 that I'll scan in with the rest of the lecture examples, but I just wrote it down. I somehow missed it when I was transcribing my notes into examples. So you guys don't forget, we have a quiz today. Opens up at 3 o'clock today. This is 3.1 and a little bit of 3.3. Excuse me. Let's see. We're going to go through 3.5. We're going to start that today. That's going to be done over a couple of days because there's a lot of stuff to think about. So I'll do like half of it today, and then we'll do another half of it on Monday. And I'll try to leave some time at the end of class, 5-10 minutes or so that I can answer questions on homework problems if you guys have them. Okay, so let's kind of keep that in mind about stuff that's coming down the pipeline. All right, so chapter 3.5 is a really neat chapter because what we're going to talk about is volumes of revolution, right? So when we think about volume, right? Think about my three-dimensional shape, right? I've got an area of the base times the height, say, for example. And what we're going to do today is we're going to have some kind of a function. We're going to take that function and we're going to rotate it or revolve it around an axis. We're going to focus on horizontal and vertical axes. So we're going to rotate around a horizontal and a vertical axis. Mostly we'll be looking at things that are either the x-axis or parallel to the x-axis, or we'll look at things that are the y-axis or parallel to the y-axis. We'll do a little bit of vertical axis stuff today. Mostly the vertical axis rotations we're going to do are going to be taken care of on Monday. Okay, so just going to keep that in mind, stuff that's happening. So it's pretty neat stuff. All right, so let's start chapter 3.5. Oops. There. So chapter. Okay, so this is volumes of revolution. Okay, so let's do a quick review when we think about volume. Make sure this is in focus. Oh, that's worse. Okay, so let's think a quick review about volume. So volume, we'll do volume of a right circular cylinder. So that's got has a circle. I'm not a great artist, but has a circle for the top, has some kind of a height, and has a circular base, right? And it has some kind of a radius. It has a radius, right? So when we think about our volume, we're going to do area of the base times the height, right? And our height is right here. Okay, so our area of the base, this is a circle, so our area of a circle, pi r squared times our height, and that's going to give us our volume, right? So this is pretty straightforward. This goes back to our geometry days, right? So that's not so bad. But what do we do for a volume if the shape isn't a regular shape, like a geometric shape? So if the shape isn't regular, how are we going to get the volume? Well, remember, it's still the same idea as we would for the area of the base times the height. So our volume is still going to be the same, but now what happens is if the base, say I've got, this, it's defined as like a function, and say I've got some other function, I'll just draw it out like this. This is my g of x. Now I've got some kind of a height. So this forms like the, let's draw our g of x like that. So, and I'm going to try to make this look like I did here. So there's my f of x. And here's my g of x. So this forms like the height of our of our shape. Let's see if we can think about how we're going to look so that this looks like this is a base here. Now, when we're doing this stuff, I like to make drawings because it helps me visualize stuff, okay? But, and I can kind of think about, there's like a height here. So we've got a height, and we've got these two functions that are intersecting with each other. So we can say our base is defined as area between the two functions. So this kind of stuff we did towards the end of Calc 1, right? When we're thinking about the area under the curve, right? So we talked about like the area between a function and the x-axis, or it could have two functions and the area was upper function minus lower function. That gave me the area between them. So that's what we're talking about here, right? So just arbitrarily speaking, g of x minus f of x, right? Without knowing which one's upper, which one's lower. So still the volume is going to be area of base times the height, right? So we've got our two functions that are being subtracted, right? And then we're going to multiply that by the height. So this is just kind of a geometric review, right? We're increasing the complexity as we go. Now, if we think about a volume of revolution, right, a solid, we're trying to calculate the volume of revolution, right? We're going to revolve a function. We're going to revolve a function around an axis. We're going to revolve a function around an axis. So we start with a function, whatever it is, f of x, g of x, something, and we rotate or revolve around, oops, the y-axis. This will be our vertical axis, or say an x-axis, or some other horizontal axis. Something that's parallel. Now, we're not talking in this class right now about if I have things at an angle, right, and I'm going to revolve around that. We're not doing that. It's sort of outside the scope of this class here. We're talking about things that are parallel to the x-axis or parallel to the y-axis. All right, so let's go around a vertical, which in this case I'll do a y-axis. So I'm going to draw it out. Like, I just want to mention drawing out, like coming up with a sketch of things is going to really help you visualize the math and what you're trying to do. And I will tell you, no one's going to grade your sketches. Okay, the sketches are just for you. Okay, which is good for me because I'm not a great artist when I draw these things out. But let's say I've got my function. So here's my function. Let's say it goes on and on, but I'm only looking from say A to B, right? So this is my function. And I want to go around the y-axis. I always like to draw. When it tells me in the problem, we're going to revolve this around the y-axis or the x-axis or something other vertical or horizontal. I always like to make a marking. Where am I actually revolving this around? Because it's going to help me visualize it. So you can think about this function here. As I take this, I'm going to sweep it out. Right? It's going to come outside the page. And it's going to revolve and it's going to go back. Like you can imagine if this axis here were just like standing up in space, then I revolved it around, okay? So as it revolves around, it's going to make a circle. And I'm going to get this other, I'm going to draw a little bit lighter. So here's my f of x here, and then this goes in the back, okay? So really what we have is, right, this three-dimensional shape that we're creating, okay, as we rotate around. It becomes a cone, right? So I create this circle. This is my axis. I create this circle in space, right, which becomes a cone. So this is a linear function. As I rotate it around, it becomes a cone. So makes a solid, whoops, makes a solid, right? And in this case, it's a cone. Okay, this shape isn't going to matter because the method for integrating is going to depend on what we're working with, whether it's a vertical axis or a horizontal axis. We'll do, and then I'll do the x-axis here as an example. Right, so here's my x-axis and my y-axis. Now we said we're going around the x-axis. I'm going to make a little note. We're going to tell you in the problem which axis where we're going around. Okay, so let's say I've got this function, right? So this is f of x. In this case, you know, it's going to be like a half of a circle. I just happen to be making geometric shapes here, but just to show you. So if I take this and I take this half circle and I sweep it around my x-axis, I'm going this way. I'm going to sweep it. Remember, we're going around a horizontal axis, so I'm going to sweep this function around my axis, right? So that means as I go around, right, and sweep it around, what I'm basically creating, right, is a three-dimensional shape. So I've got this, actually we're sweeping it this way, so I'll go this way. Right, so I'm sweeping it around that way. I've got this three-dimensional shape, which has, as its cross-sectional area, it has a circle at its cross-sectional area. Okay, so basically when I take this half circle and I sweep it around the x-axis, I'm going to create a sphere. Makes a solid, which in this case is a sphere here. Okay, I'm basically, as I'm going around, I'm creating these circles because I'm taking this function and I'm sweeping it around. Okay, so I've got this cross-sectional area of a circle that I'm working with. Okay, just kind of get you to think about what it is we're trying to do. Okay, we're thinking about basically these areas that get swept out, right? That get swept out as we're moving our function around whatever axis we're trying to rotate it around. So our goal is, right, I've got this function, I'm rotating around some horizontal or vertical axis, and I want to be able to figure out what's the volume of this new shape that I've just created by doing this revolution around my axis from x equals a to x equals b, say, for example. Okay, so to do that, we have a couple methods for allowing us to calculate the volume. We have two methods that we're going to talk about here. When you get into Calc 3, you're going to learn something else, okay, which involves basically multiple integration, right? Multiple on a function, functions of multiple variables. We're going to learn this one is called the disk method. Depending on how many functions we have, is also called the washer method. The washer method is based on the disk method. Okay, so this one is really good. We're going to be integrating cross-sectional area and these shapes of cross sections. Right, they have they're basically circles that we're creating as we sweep it out. This is good for rotating or revolving around horizontal axis. Right, so think about your disk method, right, when you want to go around an x-axis, okay, or something that's parallel to the x-axis. The other method is called the shell method. Some books call it the cylindrical shell method. It's the same thing, shell method. Okay, and this is also, we've got these cross-sectional areas. They're also circles. It's not really an area. It's sort of like it's like a let's see, cross section. I'm going to think about this. We're going to do basically little cylinders with diameter, height, and thickness. we're going to calculate this. So this is good for rotating around y-axis or vertical. So this is like when I have, and I want to go this way. Okay, so we're going to use the shell method. Today we're going to talk about the disk method. We're going to work through examples on that, disk and washer. Okay, so we're basically going to focus on horizontal, although the last example we'll do is using the disk method to go around the y-axis. You'll see how that changes and what we need to do. And then on Monday, we're going to pick up talking about the shell method, okay, which is basically dealing with, you know, these circles of varying heights, okay, that have a given diameter and a given thickness. Okay. All right, so today we're going to focus on the disk method. So let's talk about it. Disk washer method. Okay, so first, right, we're going to talk about first just the disk method. And the disk is like, you can think of, we've got this stack of pennies, right, all lined up, and we want to, but imagine if your penny was like, had varying heights, right? So the stack of pennies, they have a thickness, right? And they have an area, cross-sectional area. We're going to sum up all of those areas. Okay, so what we're going to say first is the function that we're going to be rotating, our function is continuous on our interval that we're looking at. I want to be able to find what the volume is by going from x equals a to b. Okay? Or as we talk about in our last example, y equals, say, c to d, for example. So what we're going to do is when we rotate or revolve around our axis, we create a circle. Okay, and this circle has a cross-sectional area. It's just pi r squared, right? A circle, pi r squared, okay? And so what we can do, we can add up all the areas of all the circles from A to B, right? When we say add up, we really mean integrate, because these circles have like an infinite thickness, right? They're infinitely thin. We've got this tiny, tiny, tiny little thin circle, right? And I'm going to add all of those up from A to B, and that's going to give me, in the end, a volume, okay? All right, so let me draw a picture so you can see what I'm talking about. So let's say, for example, here's my y-axis, here's my x-axis. And now I'm going to go around my x-axis, okay, just to kind of visualize. So my function, let's say, I'll draw, let's see, I'll draw my function in purple. So my function itself, here's my function. So as I take this and I revolve around my x-axis, you can imagine, I'm going to get this like mirrored image here down, right? And now as I go, I'm creating this circle. I didn't draw this very proportionally. And we're looking at A to B, okay? So within this, right, I've got a radius, okay? But my radius is changing. You can imagine here's a radius, here's a radius, here's a radius. So my radius, right, is really just the difference between my function and the axis that we're revolving around. That's the height, right? Where are we revolving? That's our x-axis and our function. Okay, so our function minus 0, right? Y equals f of x minus y equals 0 gives me my radius. So I've got all of these circles, right? And this thing is really just a solid, okay, as I'm trying to rotate it around. You see what I mean? Like, no one's going to grade you based on your picture, but it's going to help you visualize what it is you're trying to do. So let's write down. So our radius is equal to the radius of circle. So we'll say r equals the radius, which is the radius of the circle that happens when f of x revolves or rotates around our x-axis, right? So the radius r is actually equal to the height of our function. So it's this distance right there, okay? At that particular x value, right? I mean, it's not a constant. F of x isn't a constant. It's changing. So f of x has a height here at this x value. Has a different, you can see I've got all these different circles because they all have different radii because my function is changing as x goes from a to b. So I'm going to put all that together to come up with my volume. I'm going to integrate, I'm going to add up all of those circles from a to b, pi r squared dx, which is really equal to a to b pi, my function of x squared dx. This is my volume of revolution using the disk method as I go around a horizontal axis. I'll let you finish writing that and then we'll do an example. This is example 0 that I had up before that I'll scan in because I forgot to type it up apparently when I did these. I guess we're going to use our disk washer method. I don't know if you guys are done writing. I can't. Are you all set with All right. So example 0 says we're going to calculate the volume of the solid obtained by rotating the region under the graph, the function y equals x squared, our general parabola, about the x-axis. And we're going to go from 0 to 2. That's x equals 0 to x equals 2. So like I said, I always like to graph these out just to visualize. So here's x. We're going around the x-axis. 1, 2, 3, 4, 2, 4. Okay, so I'm going to go 1, 2. So I'm going to go from 0 to 2, right? I'm going to rotate this. So let's just go ahead and plot. Oops, sorry, that's not right. This is 2. And this is -2. I can count. So here, 2 to 4. So my parabola goes like this. Now, you know, the parabola goes off, right? But I'm just going to draw it from 0 to 2 because that's all I'm told to worry about. Now I'm going to create a mirror image going down just so that I can visualize it. Okay, but this is my function here. So this is my f of x. This is what I'm rotating around. So when I rotate this, I get this shape right here. So I have all of these circles as I go. Okay, so my radius on here that's the radius of my circle. Okay, it's the radius in the outermost circle, right? I'm going to have all these different radii as I go from 0 to 2. So let's set it up. Volume. We're going to go from 0 to 2. So this tells us where we're going to integrate our bounds of integration. Pi r squared dx. 0 to 2 pi. My radius is my function x squared. Don't forget to square it. Don't be lulled into a trick. This x squared is our function. We have to square our function. Okay, which is equal to pi. Remember, x squared, I multiply these exponents. This becomes x to the 4th, which now I can just do my power rule when I integrate. So I'm going to get pi x to the 5th over 5, and I'm going to evaluate that from 0 to 2. Okay, pi over 5, 2 to the 5th minus 0 to the 5th equals 32 over 5 times pi. That's my volume of this bell-like shape that results when I revolve y equals x squared around the x-axis going from 0 to 2. It's in cubic units, whatever our units are. We're generally not given units on these things. Okay. So that's setting up the disk method. washer method we're going to talk about right now, it's really similar. It's based on the disk method. We just have two functions. So we have an inner and an outer radius. You guys all set with this example here? Can I move the page? Okay, so let's draw a picture to talk about the washer method. I like my pictures. All right, so the washer method. Okay, so this is, I'll just write it down in words. So this is similar to our disk method, except that we have two functions, and that we're revolving together, two functions, and the solid of revolution has basically a hole in the middle, right? So you remember our let's do a cross-sectional view. So this is like a washer in from a hardware store, right? Our washer looks like this. Okay, so the area, so like I've got these two functions, I'm going to rotate them both around a horizontal axis. Okay, and what I have left over is this shaded region right here. So I'll do this in orange here. So there's my shaded region, right? This is the area that I'm going to be calculating all of these cross-sectional areas for. I'm going to sum them up to make a total volume. So from here to here is our inner radius. And then from here to here is our outer radius. Okay, we have an inner radius and an outer radius. These come from the distances between our outside function to the axis of revolution and our inside function to the axis of revolution. We're going to talk all about this stuff. Okay, so let's do, this looks like this from this is the cross-sectional view. So if I do this in my XY plane, right, I've got, let's see, I'll do my outer function in purple. Here's my f of x, and then my g of x I'll do in green. Right, and my cross-sectional area, and say I'm going to go from A to B, for example, right, I'm going to this right here. Okay, so when we did in Calc 1, we said, what's the area between x is equal to a, x equals b, between these two functions, right? We said upper function minus lower function. That gave us this cross-sectional area. Now imagine if I take this and I revolve this around my axis. So if I revolve around say the x-axis, this is like a horizontal axis. So if I revolve around the x-axis, what does it look like? Right, because we want to go this way. So let me draw up, give my shape. Okay, and this is going to go, here's my reflected, because I need to, let's get those. This is my f of x. So, and this goes from A to B, for example. So what do I get? I'm going to go like this. I create an outer, and I have an inner. So there's a big hole in the middle, right, like there. So the area that we're looking at It's right here in orange. I don't know, I find these visuals very helpful to think about what I'm trying to do. Okay, so we've got this, we're revolving it around the axis. Okay, so right, I've got this function here, these two functions with the orange area. I'm going to take them, I'm going to rotate them around the x-axis to get this. If I were to take this and turn it and look head in, right, so my x-axis is coming straight out of the page here, I've got a ring and a hole in the middle, okay, where I have an inner radius. Okay, so my inner radius is going to be here, right? So this is my R inner, and then my outer radius, I'll draw it from here to here. My outer radius is right there. Okay, that's my outer radius, right? So we need to be able to come up with a way to represent the area, the cross-sectional area, just the shaded region. Okay, so let's take a look. So the area of our shaded region is going to be, it's a circle. So pi r outer squared minus pi r inner squared, right? So this is the area of the outer circle, which would be a whole solid circle, minus the area of our inner circle creates just that area of that washer, that donut, okay? So now our volume is gotten by adding up all these cross-sectional areas. Areas from A to B, from x equals A to x equals B. Okay, so let's write down our formula for that. So this is going to be volume. We're going to go from A to B, right? I'm going to factor out the pi. So if I go pi outer minus pi, oops, sorry, I said I was going to factor it out, r squared inner. So I factor out the pi and I get my outer circle minus my inner circle. And this is done with respect to dx. Dx is the thickness of that little circle, that cross-sectional washer, right? It's infinitely thin, which is why we're going to sum them all up from A to B, okay? Which in this case, right, for our example here, is going to look like pi, I'm going to go f of x squared minus my inner function, g of x squared dx, and this is our volume. When I have like a couple functions, sometimes it's hard to visualize, and like I said, nobody grades you based on your drawing. It's going to taking that like 3 seconds to come up with a quick sketch is really going to help you visualize what you're trying to do. Okay, so this right here is something to think about. I also want to write down very carefully. So this is not, no, this is not f of x minus g of x quantity squared. This is not the difference of two squareds. No, 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 don't do that. Okay, this is f squared minus g squared, right? Think about pi r squared minus pi r squared. Okay, not this one. I see, that's why I see this every now and then. That's why I'm pointing this out. You don't want to make that mistake. Okay. So you've got sort of a geometry in our mind of what we're trying to do. And now we're going to try examples so we can apply it and then think about it. Okay. You guys all good with the drawing here before I turn the page? Okay, so example 1, we already did example 0. Example 1, find the volume obtained by revolving the region between this function, x squared plus 4, and that function, y equals 2, about the x-axis. And we're going to go between x equals 1 and 3. All right, so I'm going to graph this out, x squared plus 4, x, and I'm just going to draw, we're going around the x-axis, so I'm going to do a quick, like that. So I think I'll count up 2, 4, 6, 8, 10, 12, 14, minus 2, 4, 6, 8, minus 10, 12, 14. Okay, so y equals 2. Y equals 2. And then I've got x squared plus 4. So I'm going to start here. This is my parabola, but it starts here. So then let's do this. 1, 2, 3. So we're going to go from 1 to 3 is our bounds, right? Our bounds of integration. So let's see, x squared plus 4, so it's going to be like that. And then 2 is going to be there. And there's going to be there. So our parabola roughly goes like this, which means let's draw out our graph. So this is the mirror image. I'm just going to draw this really lightly. This is our mirror image, y equals, like if I'm going to rotate, y equals 2. It's going to hit this line right here, which means I'm going to get here, here, there, and there. Okay, so we've got our functions. We're going to go from 1 to 3. So from here to here, I've got my outer function, and I have my inner function, and I have my outer function, and I have my inner function. Okay, so I'll keep the color scheme consistent with what we've done before. So this is our washer, right? I've got a hole right down the middle, right around that, between y equals 2 and y equals minus 2, right around that x-axis. I've got an empty hole, and I've got all these cross-sectional areas, okay? But we're only going from 1 to 3, because we were told just to look at x equals 1 to 3. All right, so let's take notes. So our outer is equal to this. This is x squared plus 4. So that's equal to x squared plus 4. Our inner, this one here, y equals 2. Okay, so our volume is going to equal to pi. I'll factor the pi out. 1 to 3. This is our squared outer, our squared inner, dx, 1 to 3. So this is going to be, right, I'm going to go x squared plus 4 squared minus my second one, 2 squared, dx. So I have to FOIL, square this number, combine all like terms, and then I can just integrate using the power rule. So let's go ahead and do that. So that's pi, integral from 1 to 3, x to the 4th plus 8x squared plus 16. That's my x squared plus 4 squared minus 2 squared is 4 dx. Okay, so let's clean that up. This is going to be x to the 4th plus 8x squared plus 16 minus 4, that's 12 dx. Okay, so power rule when I go to integrate this. So this is pi. This is 1/5 x to the 5th. This is 8/3 x cubed and 12x. And we're going to go from 1 to 3. Okay, so I plug it all in. I do the fundamental theorem of calculus, and I did it as a fraction. You can do it as a decimal in terms of pi. Leave it in terms of pi unless you're told otherwise. Okay. If you're told to come up with a number not in terms of pi, go ahead and multiply through by use your pi button to come up with a more exact number. Otherwise, just leave it. You can do decimal times pi. That's totally fine too. Okay. Okay. You guys think, are you good with this? Have you finished writing? Okay. All right. So let's try another example. So we're going to revolve around the horizontal axis that's not the x-axis, right? But it's still it's going to be parallel to the x-axis. So we're going to find the volume obtained by revolving the region between this function, 9 minus x squared, and y equals 12, about the line y equals 15. We're going to go from 0 to 3. So I'm going to graph all this stuff out just because I like to picture it. So here's x. I think 3, 6, 9, 12, 15, 18, 21, 24, 27, 30. All right, so let's start out what we have. So about the line y equals 15. So this is our line y equals 15. This is what we're going around. So that's my first thing I want to plot out. Okay. And we're going to revolve the region y equals 12. So this is one of our functions, y equals 12. And then let's start putting in our numbers. This is 1, 2, 3. We're going to go from 0 to 3. Okay. So now 9 minus x squared. So this is equal to 0. So go 3. So we're basically going like this. Okay, now I'm going to create a mirror image on the other side of my axis, just so I can create my graph. Okay, because these are my two functions here. I'm going to take this area between these two curves, right, between 0 and 3. And I'm going to take that area and I'm going to rotate it around, excuse me, and then I'm going to have like an open space right here. But let's create this so we can visualize. So this is my other line that's going to create my inner, well, I'm sorry, I should draw it here. There. And then I've got my other circle here. Here and there. Like that. And then here's our outer. Okay. So this is 9 minus x squared, and that's y equals 12. And let's do this. Oops, yeah, that's good. Okay, so our cross-sectional area is this orange thing here. Okay, and we've got these, right? We've got this empty gap, this air gap, right, in between, this little circle in between. Okay, so remember, let's remember. So our volume, we're going to go from 0 to 3. I can pull that out right away. I'm going to do outer minus inner dx. So I had to think about what my outer is. My outer is going to be dominated by this 9 minus x squared. But watch, I've got my, let's draw this out. So I've got this axis here, right, from here up to there. So there's my outer. That's my outer radius, right? But what I'm looking at is I've got this function minus this function here. So I'm going to go from 15 minus 9 minus x squared, which 15 minus 9 plus x squared. So this becomes 6 plus x squared is my outer radius. My inner radius, okay, I'm looking at here to here, my inner radius. Okay, that's why the picture can help you. No one's going to grade your picture. So 15 minus my function, my other function, which is 12. So my inner radius is only 3. Okay, it's a straight line, right? So that's why the radius is constant, whereas this is a curvy line, so the radius is going to change depending on our x position. All right, so let's put it together into our volume equation. So we're going to go from 0 to 3. We got pi r squared minus pi r squared. So my first function is 6 plus x squared minus my inner 3 squared dx. Okay, so I have to FOIL this out, square that, combine all the like terms. 0 to 3 pi, so let's do that. So this is going to become 36 plus 12x squared plus x to the 4th minus 9 dx. That's 9 comes from here, so we can combine the 36 and the 9. Okay, and I'm just going to integrate using the power rule. So this is going to be pi times 27x plus 12x cubed over 3 plus x to the 5th over 5 from 0 to 3, which is really, let's clean this up here. Right, 12 divided by 3, 4x cubed, x to the 5th over 5 from 0 to 3. Okay, and then you're just going to do fundamental theorem of calculus, and I found this fraction here in terms of pi. Okay, be very careful. It helps to find the outer and the inner radius separately, especially when we have multiple equations that we're working with, and especially when I'm revolving around a radius or around an axis that's not the x-axis. Okay, so, and also in this case, right, I'm taking my upper minus my lower. Can't see what I just did. My upper minus my lower. Okay, so that's why we did 15 minus 12 or 15 minus 9 minus x squared instead of the other way around, upper minus lower, to calculate that area. Okay, so that gives us our volume. Okay, so far so good. All right, so our last example is using our disc and washer method to revolve around the vertical axis. Okay, so we're going to use the washer method to do that. Actually, it'll be the disc method. There are some things that we need to change, some things that we can do. It happens that this function I can convert. We're going to talk about what I mean. But in a lot of cases, when you're dealing with going around the y-axis, it's not going to be possible to convert this in terms of x equals some function of y. All right, let's draw this out so you can see what I'm talking about here. So now we're going around the y-axis. So I'm going to draw that, right? And I've got 1, 2, 3, 4, 5, 6, 7, 8, 9. 1, 2, 3, minus 3. So here's my function. This is 9 minus x squared. And I'm going to take this and I'm going to go around my y-axis, right? So if I go around the y-axis, right, what happens when I sweep this out, right? And I get this circle as I sweep it out, okay? So I'm going this way. I get all these cross-sectional areas. They're circles, right? And I'm going to add them up, going from y equals 0 to y equals however high I need to go, okay? So instead before, when we were going around the x-axis, I had my cross-sectional areas were this way. My cross-sectional areas are now like flat, right? They're laying like, you know, parallel to the x-axis. I'm going to sum them up. They're stacking one on top of each other. So there's some things I need to do first. So the first step that I need to do is I have to change the boundary of integration, the bounds of integration, since we are now adding up all the circles from bottom to top. Right, so that means that x equals 0 to 3 becomes y equals, right, when x is equal to 0, right, well, x equals 0, it's 9, but we're going to go in the other way, 0 to 9. So I'm going to go x equals 0, I plug in x equals 0, plug in x equals 3, and I find my bounds from 0 to 9. So we're going to integrate from y equals 0 to 9, not x, because we're summing things up this way. Okay, we're going to sum up all those, which means that my next step involves needing to convert my function from y equals something to x equals something. Like I said, it happens that this function I can do that with, but there are some functions that are too complex and I can't do that, which means we're going to need to use the shell method. We're going to learn that on Monday. Okay, so now I need to solve function to be x equals function of y. Okay, so I'm going to say y equals 9 minus x squared. I'm going to subtract 9. Y minus 9 equals minus x squared. I'm going to divide by minus 1. I get 9 minus y equals x squared. I take the square root. We're talking about just the positive aspect of it. Okay, so I just want the positive. So this is going to be plus 9 minus y equals x. So this is our function that we're going to integrate. Okay. So our step 3, we're going to calculate the volume. Okay, so the volume, remember, just like we did before, we're going to go from 0 to 9 pi r squared dy now. Okay, so this is, remember, our r squared is this function here. This is my r, this is my r. So let me draw that out here. So my r, that's our r, right? So this is our r, that's our r, these are our r values. Okay, so they go these horizontal slices. Okay, so let's sum these up. So I'm going to go 0 to 9 pi, right? My r, radical 9 minus y squared dy, pi r squared. Okay, it's a radical, I'm squaring it, which means I can go pi 9 minus y dy, and it's just the power rule. So I'm going to get pi 9y minus 1/2 y squared, and I'm going to evaluate from 0 to 9. Okay, so we plug this in, and we're going to get, I did this as a fraction. Okay. I want to write a little note here that step 2 may not be possible depending on the function, right? Okay, if it's not possible, then you need to use the shell method, which we haven't learned yet. We're going to learn that on Monday. Okay. All right, so I'm going to stop there in terms of new material, because when we pick up on Monday, we're going to talk about the shell method. I want just to kind of have a nice break here in terms of ideas. So that leaves us, about 10 minutes or so, or a little bit more than 10 minutes to answer some homework questions. So I can answer homework questions on 3.1, 3.3. Remember, we have a quiz on that in about a half hour. So you guys all have this here. I'm going to move this 3.3 number 21. Sure. Okay. Give me a sec. Okay, the arc length. Yeah, so the arc length, this one, okay, we'll set this one up. So this is chapter 3.3, number 21. So this is an arc length problem. Okay, so we're going to calculate the arc length over a given interval. So we're given our function g of x equals natural log of the sine of x in the interval that we're talking about, pi over 4, pi over 2. Okay, so remember our arc length is going to look like, we're going to go from a to b, square root 1 plus dy dx, in this case, squared dx. Okay, so I've got my function here, right? This is my y equals g of x. So I need to take my, my derivative. So my derivative of this is going to be 1 over the sine of x times my chain rule cosine of x, which is my cotangent. Okay, so I need to square that and put it in here. So so I'm going to go from pi over 4 to pi over 2, and this is 1 plus cotangent of x squared, square rooted dx. So 1 plus the cotangent squared of x is an identity. It's a Pythagorean identity. Remember, it starts off with sine squared plus cosine squared equals 1. If I divide everything by sine squared, right, then I get 1 plus cotangent squared equals 1 over sine is cosecant. This becomes cosecant squared of x. So I can just substitute that in here. So this is pi over 4, pi over 2. This becomes cosecant squared of x, which, because it's squared inside of a square root, this is really cosecant of x dx. Now, let me just tell you ahead of time, on an exam, if you had this, you could just say, we usually ask you these things, and we just ask you to set it up and leave it. I'm going to just keep going and solve it. I don't expect you to know off the top of your head, like how to integrate the cosecant. You can look it up in a derivative and integral table for this, but basically the integral of cosecant comes out to be minus the natural log cosecant of x plus cotangent of x, absolute value, and we're going to go from pi over 4 to pi over 2, which now, if I'm going to evaluate this, this is going to be minus natural log cosecant of, pi over 2 plus cotangent of pi over 2 minus a minus cosecant pi over 4 plus the cotangent of pi over 4. So you have to remember your trig. So cosecant is 1 over sine. Sine of pi over 2 is 1, so this is 1, plus cotangent of pi over 2, this is 0. So this is minus ln of 1, which becomes 0, plus ln. Cosecant of pi over 4 is radical 2. Cotangent of pi over 4 is equal to 1. So this is our answer here. Okay, but like I said, I worked through the rest of it. It would be helpful if, like, you looked it up in a derivative and integral table to find out you know, what's the formula for cosecant, but normally when we do these, we leave it in terms of that. So we will tell you to just leave it if we want you to. If we expect you to work it through, we won't say anything. We'll just say, what is it? What's the answer? If we say, set up the integral and leave it, you don't have to solve it, then you're good to go. That's how you'll know, because we'll tell you. 3.1, number 32, sure, let me get that out. Okay, so 3.1, number 32, looks like this. So we want to calculate the total distance traveled. And this is a particle going in a straight line. So we've got between t0 and t, and we've got t is greater than t0. I guess they're not giving us, what do I have? Okay, t0, so t is greater than or equal to 3, it looks like. So they gave us t0 equals to 3. So they give us our velocity, which is t squared plus 7t minus 18. So what I need to do, total distance traveled, is we're going to go from 3 to t. I have to take the absolute value of my velocity, right? So this is a straight line. So this is my parabola, right? So I can actually graph this. So I can go x minus 18, and I graph it. It looks like this. Looks like I have a sign change. So my function does stuff here and here, which I can now, I'm going to factor this to find out where the sign changes, because it's distance traveled. So I have to find out where to split up my integral and where to multiply by -1. So I'm going to factor this. So I'm going to get, when I factor this out, this is, I can do my quadratic formula. I was going to guess and check, but I'll just do quadratic formula. So minus b, so minus 7 plus or minus b squared minus 4ac and all over 2. Okay, so if I go 49 plus 4 times 18 is 121. So this is minus 7 plus or minus 11 all over 2. All right, so we're looking at, so t equals minus 7 minus 11 is minus 9, minus 7 plus 11 is 2. So we have sign changes at minus 9 and positive 2. So what that means is we're actually outside of a sign change. So I don't need to break up my integral just because of the way that they defined this t greater than 3, right? It's happening outside of that. But I do need to find out, is it positive or negative? So if I plug in, I'll check this one here. So if I plug in v of 2 squared plus 7 times 2, oops, sorry, that's going to give me 0. Let's do 3, sorry, my bad, because I'm going to check the beginning here, minus 18. Okay, so I've got, I'm looking for, I know I have a sign change at 2. Let me see what happens at 3, because that's where they told me to start looking. So I'm going to get 9 plus 21 minus 18. I already know this is going to be positive, right? So that means that we don't have to multiply by a -1. We can just integrate as normal. So I'm going to go from 3 to t. So t squared plus 7t minus 18 dt. So it's just power rule. Right, so that's 1/3 t cubed plus 7 halves t squared, 18t, 3 to t. So I'm going to plug in t minus, I'm going to plug in a 3 right. So this one, what did I get when I did this? 32. All right, so I'm going to get 1/3 t cubed plus 7 over 2 d squared, 18t plus 13.5. And this is my total distance traveled as a function of time. They don't tell me like numbers, what's the actual intervals. So I'm really just dealing with an equation. I'm going to get an equation because I go t from time t equals 3 to some arbitrary t value. Okay, and number 24 on 3.3. Okay, so arc length. Okay, so this one's actually got a lot of algebra on it, which I'm gonna leave the algebra up to you. I'll set it up and then you guys can do the algebra. There's a lot of like, finding common denominators and factoring and stuff on 24. 3.3. So it'll be good practice, but I'll tell you how to set it up and then I'll give you the answer so you can check it. So your function is x cubed over 12 plus 1 over x, and our interval is 1 to 2. So remember our arc length, right? Which is what we're being asked for here. Our arc length is going to be a to b 1 plus our derivative squared, square rooted dx. So I need to take the derivative, right? It's going to be 3x squared all over 12 minus 1 over x squared. So this is x squared over 4 minus 1 over x squared. Okay, you may find it helpful to combine this, find a common denominator and combiner, however you want to work the algebra. So our arc length, we're going to go from 1 to 2. X squared over 4 minus 1 over x squared squared, square rooted dx. Okay, so there's a lot of cleanup here. I had to do a lot of cleanup on here. I'll give you a hint. Lots of algebra. Okay, it's going to be a black box because I'm not going to go through it all. You guys can take a look at it. Basically, what I got was I ended up integrating 1/4 x squared dx plus 1 over x squared dx. So there's lots of algebra to get to this point here, which then is going to give me antiderivatives of 1/12 plus minus 1 over x, right? And then when you do this, you're going to get, I got 13 over 12 as a final answer. Okay, so I'm skipping all the algebra so that you guys can practice that. Practicing algebra is good, but at least you know where you can aim. Okay. All right, you guys, have a great weekend and try the 3.5 homework. I'll scan in the 3.5 stuff that we've covered today, so you have a partial list for it, and then we'll regroup with 3.5 on Monday. Okay, and don't forget the quiz opens up today at 3 o'clock. Okay, have a great weekend, you guys.
Thank you.
Bye.
Thank you.
Thank you.
Thank you.
Bye. Take care.